So we're going to continue our discussion on nuclear chemistry. We talked about briefly the six different types of nuclear decay and mentioned different particles that show up in nuclear reactions. So please make sure that you are able to write and identify what these particles are. Okay, you essentially need to memorize those. And when we are using these particles in nuclear equation or nuclear reactions and balancing equations, we're essentially making sure that the mass number and the atomic number on both sides of the reaction arrow add up to the same, are equal. Okay, so mass number has to be the same on both sides. Atomic number has to be the same on both sides. And so for the most part, it's pretty straightforward, I think, in terms of figuring out what's going on with these nuclear equations. We talked a little bit about three different types of radiation, the properties of alpha, beta, and gamma radiation. So an alpha particle is essentially a helium nuclei. Beta radiation is electrons, and gamma radiation is a type of photon. Okay. We then looked at alpha emission. So this is one example is the decay of uranium by alpha emission. So uranium-238, which has an atomic number of 92, decays by alpha emission. So that means it forms an alpha particle and forms then a daughter nuclide of thorium-234. Okay. And so if we look at this chemical equation and we look at the sum of the mass numbers on the product side, they equal that of the mass number on the reactant side, and same with the atomic numbers. Okay. So if you're told that a reaction decays by alpha emission, you should know that an alpha particle is going to show up and then be able to predict the other product. Okay? And figuring out the element, the way to approach that is to first determine the atomic number and then match that up with its element on the periodic table. We're going to go through examples of the other types of nuclear decay. The next one up here is beta emission. And so this is the emission of a high-speed electron. And the nuclide symbol for an electron is going to be the lowercase e, the -1 sort of subscript on the left, and 0 superscript on the left. And so when you are thinking about what an electron is in terms of its nuclide symbol, you should be able to write this. In beta emission, that is going to be one of the products. Okay. Typically, there's an unstable nucleus that is going to be essentially the reactant that will then decay excuse me, by releasing a high-speed electron. And in doing so, this increases the atomic number of the reactant on the product side. And essentially what we do is create a proton. And the way that happens is that a neutron is converted to a proton. So let's look at the radioactive decay of carbon-14. So carbon has an atomic number of 6. Okay, 14 is the mass number. It decays by beta emission. So it's going to form that electron. And then what we are left with, so if we have to have this same atomic number on both sides, that means the atomic number of that product has to be 7. Looking at our periodic table, atomic number 7 is the element nitrogen, and the mass number does not change. So it is 14. Everyone see how we get atomic numbers and mass numbers and element symbol? Okay. So in thinking about what happens then when an electron is emitted, the mass number is the number of protons plus neutrons, right? And the atomic number is the number of protons. So 14 minus 7 is going to give us 7 neutrons on the product side. 14 minus 6 is 8 neutrons on the reactant side. And so, as I said, with beta emission, a neutron is converted to a proton. And you can see we're short one proton, one neutron, and that has been converted then to a proton. Okay. That makes sense? Okay. Gamma radiation is kind of a neat process. We actually utilize the gamma radiation in medicine. For instance, in any kind of medical imaging where you have to take like a radioactive drug that is then used for imaging, that's collecting gamma radiation. One of the examples of that is technetium-99, so TC-99. In medicine, we use a metastable technetium-99, so we put a little M here to signify that it's metastable, and metastable essentially means that the nucleus has too much energy. Okay? And so technetium-99, and I'm going to put a little M there for metastable, atomic number 43, can decay by gamma radiation to form technetium-99. And this is still technetium, it still has atomic number 43, but it gives off gamma radiation. Gamma radiation has 0 mass number, 0 atomic number. So we have technetium on the reactant side, technetium on the product side, but essentially what is given off is a photon. And that photon comes from that excess energy in the nucleus of the technetium isotope. The way that technetium is used in medicine is that it's attracted or attached to a drug that will then be goes to the desired location in the body, and by some sort of process that involves biochemistry, will be able to like stay in that desired location and allows that location to be imaged. Okay. This type of technetium has a really short half-life, so its half-life is about 1 day. So if you have to take technetium, metastable technetium-99 for any reason, after 1 day, half of that has decayed away by gamma radiation. Okay. We'll talk a little bit more about half-lives, essentially kinetics of radioactive decay for these nuclear reactions. They all follow first-order reaction kinetics, which is convenient. That's one of the easier ones. And so we'll be able to make some predictions about concentrations or amounts using that type of information. Next up then is positron emission. So what is a positron? Positron is kind of like an electron, except that it has a positive charge. So it has the same mass as an electron, but instead of having a negative charge like an electron, it has a positive charge. We often give it the symbol beta plus, but when we're writing our decay equations, we're going to do this nuclide symbol for positron, for a positron. Okay. So there's another isotope of technetium that decays by positron emission, and that's technetium-95. right? Again, it has the same atomic mass, or atomic number, excuse me. Technetium has the atomic number 43. And when it decays by positron emission, we know it's going to form our positron, and the element that it's going to form is going to have an atomic number of 42. It's going to have a mass number of 95. Okay, so mass number is not going to change in this reaction. And so that gives us the element molybdenum. So hopefully you're seeing a pattern here with these types of decays. We take an isotope, we figure out what kind of emission is going to happen. We can write that nuclide symbol, and then using some addition and subtraction, figure out what the daughter nuclide is going to be. So daughter nuclide being the isotope of whatever element is formed. Okay. Questions on any of these so far? Yeah.
How does the atomic number decrease?
So it is decreasing because essentially it's going to eliminate a proton through this decay. So we're thinking about like mathematically, it's just as simple as it has to be 42 because the sum of this number and whatever this number is going to be has to be equal to this. But essentially what that does is it means that we have one less proton in that element. Does that make sense? Kind of. Okay. So again, I think when we're thinking about nuclear chemistry, we have to remember that all of these reactions essentially involve the nucleus, which, I mean, it kind of sounds obvious, but it's not always. It's in the name, but we have to be thinking more about the nucleus than we ever have in our chemistry experience at this point. They're happening within the nucleus of the atom. Okay, electron capture is the next one I want to talk about. This is going to involve the decay of an unstable nucleus. And essentially what's going to happen is we're going to have a nucleus of an atom that is not stable. We're going to have an electron from an outer orbital, an inner orbital that's going to enter and be converted and going to convert a proton to a neutron. Okay, so essentially, we're going to then take a proton in the nucleus and change it to a neutron. Proton is going to have the symbol P, superscript 1, subscript 1. We're going to combine it with an electron, which has this symbol. And that was going to give us, in terms of a product, 1 in the superscript, 0 in the subscript, and that's going to be a neutron. Okay. So an electron from an inner orbital is captured by the nucleus and converts a proton to a neutron. One example of this is the decay of potassium-40. So potassium-40, atomic number 19. In this electron capture equation, now we have two reactants. Okay, we have our isotope, and we're going to have that electron that's coming from the inner orbital. Okay, we're going to have one product. The mass number is not going to change, right? Because our electron doesn't have any mass. And but the atomic number does change. In this case, we need to be 18 on the product side. And so that's going to be element argon. Okay. I think has anyone seen or heard of like trying to measure a banana with a Geiger counter? Is this a thing that y'all know about? So a Geiger counter measures radiation. And you can't actually pick up that much radiation from a banana, a little bit, but it's because of this decay, this potassium isotope, which shows up just in small amounts because bananas have so much potassium. Okay. We're going to talk about some other things. Spontaneous fission. Again, we're going to have another unstable nucleus, but instead of that nucleus decaying by electron capture, it's going to split a heavy nucleus into lighter nuclei and neutrons, and it's going to release energy in the process. So an example of this is uranium-236. This type of fission is, I wouldn't expect you to be able to take uranium and figure out what the two products of this like daughter nuclides are going to be, but you should be able to figure out the number of neutrons that are going to form. So if we take uranium-236, it decays by spontaneous fission to form yttrium-96 and iodine-136. So how many neutrons are going to be formed? Anyone have an idea, a guess? Yeah. 4, yes, thank you. So if we sum up our mass numbers on our product side, we're only going to sum up to 232. We know we can add at the end the correct number of neutrons. We're going to need 4 more to get that total mass number of 236. Everyone see that? Okay, cool. So like I said, be able to calculate or predict the number of neutrons in this type of reaction. Oh yes, question. No, I wouldn't expect you to predict those 2 daughter nuclei. So we've looked at 6 different types of nuclear decay. How are we going to be able to predict what happens for different types of isotopes? There are some ways of predicting, and one of those is what we refer to as a chart that is called the pattern of stability or the belt of stability. And essentially what this is going to do is allow us to just make a prediction based on the number of neutrons and the number of protons in an isotope. So, scientists essentially have developed this chart through a series of experiments looking at different isotopes for different elements. And so from that, we have been able to sort of take a look at those isotopes, and now we can say, okay, if we have this isotope, we can expect it to decay in a certain way. It also allows us to predict why some nuclides are stable and some are unstable. So an unstable nuclide that you're going to hear about a lot is carbon-14. We use this in radiometric dating, carbon-14 dating. But carbon-12 and carbon-13 are the stable nuclides of carbon. Okay, and so the reason we'll go into here quickly, but I want to sort of discuss what's going on in this chart. So in this chart, on our y-axis, we have number of neutrons, and on our x-axis, we have number of protons. So the number of protons we can get easily from our atomic number, but we'll need to do the subtraction between, take the atomic number, take the mass number minus the atomic number to get the number of neutrons for that isotope, okay? So that is one small calculation that you have to do in order to use this chart. And essentially what this chart is doing is allowing us to use a neutron to proton ratio to figure out if an isotope will be stable. And so what we see is as the number of protons in the nucleus increases, we need more neutrons to counter their charge and to increase the stability by decreasing the repulsions that those positively charged particles will have. When we have small particles, small isotopes, something that has an atomic number less than 20, we don't need to have an excess number of neutrons. And in that case, the neutron to proton ratio is pretty close to 1:1. Okay, so this red line in this figure shows a 1:1 ratio of protons to neutrons, or excuse me, neutrons to protons, that does matter. And so you can see that initially the stable isotopes, which are in this sort of darker, maybe blue color, follow along that red line, okay? But as we increase atomic number, which, in case I hadn't mentioned it before, is often given the symbol Z, okay? As we increase in atomic number, you notice that the pattern, the band, sort of trends sort of upward, okay? And what this is saying is that we need to have more neutrons to have a stable isotope. And again, the stable isotope are these blue or dark colored dots on this chart, okay? For those nuclei above atomic number 20, if we have a neutron to proton ratio of more than 1, we have a stable nucleus. So essentially what we will often see is that the neutron to proton ratio is 1.5 to 1. Okay, you don't necessarily need to remember that number, but that is the general trend. So there's another thing that's important to recognize with the band of stability. And that is that we can make general predictions about what types of decays occur based on where our isotope falls along this band. So for those nuclei that fall above the dark line, okay, so on this side, we typically see beta emission. Okay. So if we had a nuclei with, let's just draw one out here. Atomic number 30, oops. And then number of neutrons equals 50. So our mass number equals 80, okay? Then we should expect that nuclide to decay by beta emission. Okay? Again, I think I need to reiterate that those nuclei that are, well, no, actually, no, I'm not going to say that. Take that back. So then the opposite sort of effect here is that the nuclei that are below the band of stability or belt of stability on this chart typically decay by either positron emission or electron capture. So that's as far as we're going to ask you to know, electron capture or positron emission. Being able to distinguish and to predict which one of those is much more challenging. Okay. And then once we go or get above nuclei with an atomic number of greater than 84, oops, these nuclei tend to decay by alpha emission. Okay. So if we have atomic number greater than 84, alpha emission, above the band of stability, beta emission, below the band of stability, either positron emission or electron capture. Okay. So that's sort of a useful tool for predicting types of decay. Okay. Questions on that? Yes.
Can you reiterate what the box through the 15 and
Oh,
34 times is again?
just trying to use an example. So if we came up with, what's mass number 30, or atomic number 30, zinc. If we'd had the zinc 80 isotope, and we were trying to predict how it were to decay, it falls above that band of stability, and so we would expect it to decay by beta emission. I don't actually know if that's an isotope or if I've just chosen some easy numbers, so I actually have to look that up. I might be outside of the chart. Other questions? Okay. All right, there are plenty of radioactive nuclei that are not able to become stable after just one type of nuclear decay reaction or one nuclear transformation. A good example of that is uranium-238. Okay. It actually will undergo a series of decays before it gets to a stable nucleus. So for uranium-238, we'll take a look at our chart here. Again, on our chart, our axes, we have mass number. This time we have mass number on our y-axis and atomic number on our x-axis. We're starting with uranium-238. The first transition, or the first type of decay it will undergo is alpha emission. In this figure, it's trying to use those blue arrows to show alpha emission. And then the red arrows are going to be beta emission. Okay? So uranium-238 will first undergo alpha emission to form thorium-234. Okay. That then undergoes a beta emission to form PA as protactinium. Had to look that one up today, couldn't remember. protactinium 234, which then undergoes another beta emission to form uranium 234. From there, there's another alpha emission, and another, and another, and another, and another. And eventually we get down to the stable nuclide, which is lead 206. Okay. With a atomic number of 82. So that's the stable nuclide. And essentially what this is showing you is that there can be lots of different types of nuclear transformations that need to happen in order to get to a stable nucleus. Again, should not have to predict this. Okay, no way of doing that. Lots of science, lots of research goes into predicting that or to determining that. Questions, though? Okay. All right. Other types of nuclear reactions include what we call nuclear transmutation. So this is not a decay type of reaction. This is when we're going to take a nucleus and hit it with another particle. Okay? So a good example of this is we take nitrogen 14, smack it with an alpha particle, and we obtain oxygen 17 and a proton. Okay. So we use a shorthand notation often for this type of transmutation, where we've got on the left-hand side our target nucleus. So in this case, we're targeting the nitrogen 14 isotope. Then we make parentheses, and inside the parentheses on the left side, we're going to put the bombarding particle. So in this case, that's our alpha particle, the helium 4 particle. So we're hitting the nitrogen with the helium. And then we eject a small particle that is, in this case, the proton. And our product nucleus goes on the right-hand side outside of the parentheses. And in this case, that's oxygen 17. So make sure you're able to take this type of reaction and write out its shorthand and vice versa. Be able to recognize what the bombarding particle is, what the ejected particle is, and things like that. Okay. Now, because if you've listened or if you've heard anything about particle accelerators, this is the type of nuclear chemistry that they're doing. So Fermilab is a particle accelerator. The CERN lab in Switzerland is a particle accelerator. And they essentially use these particle accelerators to produce transuranium elements. So transuranium meaning greater atomic number than what uranium has. And you can look that up, okay? So this image here is the Fermilab, just outside of Chicago, I believe. Is anyone from that area? Yeah, have you seen this Fermilab?
No, I haven't.
Yeah, I think that's where it is. But it's huge. So this circle and this circle are the particle accelerators. So you can see it using Google Maps or Google Earth, whatever this one was. It's a huge thing. And so we use these giant circular type of reaction vessels, I suppose, to create very, very high speed particles. They're moving at the speed of light, and we need this sort of long track in order to get them at high speeds. And we collide those particles with whatever we want to react it with. Okay? An example of this is the production of curium. using plutonium. So I'll put those there. We don't usually use plutonium and curium, so I'll include their names. So plutonium-239 would be in a particle accelerator with the alpha particle. When those two collide, they form cerium-242 and a neutron. So if we were to write the shorthand of this reaction, we would put the plutonium on the outside, left side of the parentheses. We're going to bombard it with an alpha particle. A particle that's produced is the neutron, and what do we call product nucleus is the curium-242. Whoops. Okay. So both of those, the chemical equation with the arrow and the shorthand notation represent the same thing. And so these particle accelerators are the way that we synthesize new elements. A good example of this was in 2010, the formation of tennessine. I think I'm pronouncing that correctly. T-E-N-N, tennessine, element symbol TS, named after the state, Tennessee, where this particle was created. And so essentially, this took place at Oak Ridge National Lab in Tennessee. And also had a collaborator with Lawrence Livermore National Lab, which is out in Berkeley. And in fact, the US and Russia worked together on this project to create this new element. And what happened, the way this worked, I have another slide, was that a calcium-48 beam of particles were put into the particle accelerator and collided with berkelium. This is 249. To form tennessine-297 with an atomic number of 117. We're going to put a star there because it was not stable. I believe it lasted for only a few milliseconds. It then formed a different isotope, tennessine-294, 117. And how many neutrons? Yeah.
3 neutrons?
3 neutrons. Yep. So 294 plus the 3 neutrons gives us 297, which was the initial isotope of tennessine. Okay. Questions on that? Let me go back. All right. The next slide just shows the decay pattern for tennessine. So we don't need to go into that, but it does decay by alpha emission and gets to eventually to a stable particle. Okay. Questions on any of that? Friday, shorter lecture. Maybe we'll do some demos. I can bring in a Geiger counter, things like that. Yeah, that's it for today then. here. We're